Sumit? Hello, Sumit.
Yes, sir. It is done.
Okay, it is done now. Okay. Okay, so you guys already know that. Okay, so we'll just revise that and then we will see how we can code this sequence detector in Verilog. Okay, so moving further, just a short introduction. So what's FSM? It's finite state machine. Its name itself tells you that it will have a finite states. Okay, so it depends upon the specification or the functionality your system is going to execute, and depending on that we will take numerous number of states, whatever states we will be needing, that we will take, and then we will create a FSM. But what's actually it is, what's its use? So every design actually consists of a data path and a control path. Okay, so you can say it like a combinational and this is sequential. Okay, so every design is made by combination of these two. Okay, there will be some combinational structure inside your design and there will be some sequential structure. So we call it as a control path. So FSM is nothing but the control part of your design. Okay, I'm not using the word path, I'm just using part. It's like there are two parts in your design and the control part or the brain you can say, that is nothing but your FSM. So it controls the entire system design by hopping between various states a system can be in based on the inputs. So based on various inputs a machine has, like, so it can hop between whatever states. So here I've taken an example, like there is some kind of machine, you can say any machine you can take. So what can be, I take an ATM machine. Okay, so when no one is using it, it's an idle. Okay, when someone presses some button it is kind of running. Okay, so and if there is some error it will go into error state, and there is some ready state also. So it's not a perfect example, just I'm telling you that some machine or some kind of design can be in different states. So when it will be in that state it depends upon the inputs, right? So if you are trying to access the machine, giving your card, so that's all your input is, like you're giving some input and then this machine will work accordingly. So it is predefined that in what state your machine can go, that you have to design while designing your FSM. Okay, so during any system design, all the possible states are first calculated based on specifications, and then state diagram is made which covers all possible scenarios a system can be in based on its present and or inputs. Okay, on present states or inputs. So we first evaluate everything, like what are the various scenarios our machine can be, our system can be in, and accordingly we list down all the states, and then based on the inputs we kind of design a state diagram that how it will work, okay, based on the inputs. So that's what the basic concept of FSM is. Like, and it would be finite, it can't be infinite that yet you will be having infinite number of states. Obviously it will be a finite state. So there are two types, Mealy and Moore. So you already know, I will just discuss. So this is the typical diagram every textbook has about the Mealy and Moore machine. Okay, so this one is Mealy machine and this is the Moore machine. Okay, so a typical all these both two diagrams has an X state combinational logic. Okay, it's a combinational, not sequential. State registers. Okay, and then output combinational logic. Okay, so there are two combinational logics and state registers. State register nothing but a sequential logic, you can say. Okay, same the Moore machine also has, but there is a difference that in Mealy your output depends on input variables and current state. Current state is present state. Okay, just a second. Okay, fine. Uh, yeah. So in terms for Moore, output depends only on current state. So I guess in theory lectures you already know this concept. Okay, who wants to join? Guess okay, someone else was there. Okay, so these things, there is not too much explanation I think that is needed, but about sequence detector also. So a sequence detector accepts as input a string of bits, either 0 or 1. Okay, and its output goes to 1 when a target sequence has been detected. Okay, sorry. Right, so when it output will go to 1 whenever this target sequence is being detected. So we will set our sequence like we want to detect 0 1 1 0 something. So when it is detected, your output will goes to 1. There are two types, overlap and non-overlap. So we will see what this two type means. So by example, if you are provided with input bit strings, so this is your input. Okay, your machine or your design has this kind of inputs coming one by one. Okay, so and 0 1 is what you have to detect using the non-overlap method, right? So can anyone try? And that how many times you will get 1? If you have you have been taught this concept, right? If not, then I will tell you. But as you know this concept, anyone can try. You guys are clear with the question or not? Paresh, any audio issues or something?
No.
Okay, fine. No one? Okay, fine. I'm not aware that you guys know this concept or not. Let it be, I will tell.
They are given answer in chat box.
Okay, they are giving answer in chat. You can unmute, no issues. Yeah, 5 times. Okay, good. So what will happen? This is your input string and you want to detect it by non-overlap method. 0 1 you have to detect. So this will be first time. Okay, as it is a non-overlap method, we are not considering this previous one or something. We'll have to start from fresh. Okay, we'll see what's the difference. So when we have again 1 and 0 1 is not there, so here we got again 0 1, so again 1, there is no 0 1 again. Okay, when we have got and this one. Okay, this total counts to 5. So 5 times your output will be 1, right? Same question. I think input string is different, but you have to detect 1 1 now using overlap method. Can you try? Seven. Okay, we'll check. So 1 1 we have to detect. Okay, so it's overlap method. So when it will be 1 1 this time, first one, then as it is overlap, so we have to consider this previous one. Okay, so this would be your second 1 1, right? So 1 1 2 times. then this one, third, fourth, okay, fifth, right, and nothing. This will be 6 and this will be 7, right? So there will be 7 times your output will get to 1. Okay, so I think you know the concept of this overlap and non-overlap. Okay, so quickly we will go through the example to refresh your concepts of simple 0-1 detector based FSM. So what we have to do, we will try to draw its state diagram. First we will see the Mealy one. Okay, so there will be initial state, right? And for Mealy, it's like always in this kind of arrow. So I'm telling you from very scratch, right? I'm not telling you, kind of explaining this very brief manner. Okay, so input you have and then output. Okay, in this manner we are writing here on these arrows, right? So first will be in initial state. Okay, so when 1 is there, as we are detecting 1 0, okay, this is clear. As when input will be 1, right, we'll go to the next state. Okay, and output will be 0 at this condition, right? And now we have detected 1, now we want 0, right? So if 0 is detected here, you can see this arrow, right? If 0 is there, then our output will change to 1 and we are going to the initial state again. But in this second state, name it as 1, this is S0. Okay, in S1 state, if you are getting your input as 1, okay, then you will have your output to be set to 0, right? Because we are detecting 0 1, not 1 1, right? This is what happens in Mealy. Okay, so now in terms of Moore, it's slight change. What we write inside are these circles. Okay, this is state 0. So inside this circle we are kind of writing the outputs, what your output will be, right? So state we write and then we write just below it outputs, right? So this is output, this is output. Okay, so first we will be in initial state. It is kind of called as your idle state in Moore. Okay, at that time your output will be 0. Okay, and when we will get your input as 1, okay, we will go to the next state. This is my 0 state, this is my S1 state, this is my S2 state, right? So when we are, as we are detecting 1 0, so when 1 will come, then we will go to next state, and when 0 will come, we will go to the final state where we will set our output to 1. This is what you follow while doing the diagram of Moore, right? So if these are your state, if 1 0 1 you want to detect, you first write 1 here, then 1 0 if you want to detect, you write 0 here. This is your first step. Then you start doing whatever remaining states are there. First directly conclude with your detecting sequence, and then we will see what remaining states or what remaining inputs are. Okay, so we have finished with these two arrows, right? But now about this one arrow is going outside from this S0. Now we want another one. What about when input is 0? Like for 1 we are done. What about 0? For 0 it will remain in this state only, right? For this one, what if 1 we have? Okay, for 1 will remain in this one only for S1. Why? Because this state detects 1, right? If you are 1, if you are getting 1 1, then you have to remain in S1 state only. Why? This is the state which detects 1, right? And for S2, if you are getting 1, then you have to go to S1 again, all right? And when 0 is being detected, you have to go to the reset state, because you have to start from the scratch, from the beginning. You have to start detecting something. So these things will be clear to you if you practice about this. Okay, you take any sequence, you start writing its drawing its state diagram, then and then only you can be quite good with that. If you have attended 4 or 5 lectures, still you are not getting, then that means you are not practicing this part. Okay, so you have to practice, take any sequence and then practice. That will only result you in being proficient in drawing the state diagrams. Okay, so I haven't taken a good example of case statement, that's why I'm taking this one. Okay, it's for mux, right? So say you have 4 inputs to a mux, A, B, C, D. Okay, and select lines, a 2-bit select line we are having. Okay, and one output, right? Output rec, both. So always when A, B, C, D, it's like A, comma, B, comma, C, comma, D, or select any one of these. If changes, then case, see this structure, or we can say syntax. These all values are for select lines. 0, 1, 2, 3 means whatever select will be there, SCL will be there. At that time you are assigning your output as A, B, C, D depending on the values of select. So this thing we will be needing in designing our FSM. Case statement we are using, that's why I've taken this example, right? So it's just like the C case statement only, the C programming case statement, so it's nothing different. But notice that these all values are numeric, kind of whatever value SCL is taking. Okay, so you can see that whatever values SCL is taking, you can write here 0, or you can write 2 comma or 2f stroke b00. In this way also you can write, or you can write in decimal also, no issues. Sometimes simulator might give you some error, so you can try writing decimal also, but it's good to write in binary. Okay, and it's mandatory to write a default statement. Okay, and in default don't write display or something, because this is unsynthesizable, right? So you have to write this kind of, you have to keep the output to high impedance, or don't care something. It's good to keep it in on high impedance, as your output is 1 bit, so you have to keep it on Z, right? So till here, anyone have doubts, any questions?
Hello, sir.
Yes.
We have given the input like select 1 comma 0 means 1 to 2. Two select lines are there. So out case in a case means it is like a 0 0 0 1 1 1 0, or may similar to this now means like 0 1 2 3 for case statements.
It's like means this 0 is there now. This 0
Yes.
is actually this is 2-bit 0. This
Okay,
one is actually 2-B01. So I haven't used this part, means in decimal I don't generally use, I write in binary only. So
okay,
it's
sir.
better if you write in binary, there are no issues. You will see, I will give you some shortcut to write that. We generally use parameters if you are writing this, but okay, for mux it's better to write in binary format. Okay, any other question? No, I guess. Okay, so now for state diagram of sequence detector. So I have taken example of 1011 sequence detector with a non-overlapping method, and my FSM style is Moore. Okay, these 3 things you have to consider. Step 1 is check the number of states required. So how many states it would be requiring for this 1011 detector? Anyone? Yes.
4.
Yeah, 4. Right. So no, for Moore I am asking. Okay, for Moore you will be requiring 5 states, S0 to S4. You can kind of remember this like it's Moore, right? So Moore actually requires more state than Mealy. One extra state is there in Moore. Okay, so you can just omit one O from it and you can remember it like more. so it requires one more state. So as it is 1011 4 bit, so we require one extra state, that's why 5 states, right? Okay, so there are steps to follow. Anyone having doubt? Okay, so first you have to check number of states required, calculate that, then use state diagram. So while writing the Verilog code of this FSM, you must be very clear with your state diagram. You can't proceed further without having a state diagram in front of you. Okay, so step 2 you have to do first, and then I will give you kind of a syntax of this FSM code, and using that syntax you have to proceed further. Okay, so these 3 steps you have to calculate. Okay, so first we will see the state diagram. Okay, so it's a Moore FSM. Okay, so it will need 5 states starting from S0 to S4. So first you have to draw all the 5 circles, right? Name it S0, S1, S2, S3, S4, and then afterwards, what's your sequence? My sequence is 1011. So just first draw 1, then 0, 1, 1. Okay, these are your initial arrows. That's the method I generally follow. So 1011 you have to write. Okay, then you see the remaining inputs, right? These are all your inputs, 1011. So when you will get your final one, at that time your output will be 1, right? These all are outputs, right? So you will get output as 1 in your final state only. Now what's remaining? Now for this S0 state, 1 is already being, for 1 we know to what state it will go, but for 0 it will remain in this state only for the initial state, right? Now take this second state. For 0 input we know it is going to some another state. What for 1? For 1 it will be in the same state. Why? Because this is the state which detects your first one, so it will be in this state only. Now we know for S2 what happens if 1 is there, but what about 0? If 0 is there, it will have to go to the previous state, the S0 state, initial one. Why? Because if you are standing at S1, you have detected 1 0, but now what you are getting 0, that is right. You have detected this, but you are getting 0. Then you have to start from scratch again. Okay, so you are now being given, means you have hopped to the S0 state, right? Similarly for S3, if you are getting 0, you have to again go to the initial one, right? Okay, and for S4, for S4, whether it's a 0 or it's a 1, if it's a 0 you have to go to S0, and if it's a 1 you have to go to your 1 detector S1 state, right? So this was the FSM for your 1011. Okay, I guess you can draw this, you can take a snap of it. It's better if you draw it by your own. Okay, so now we will see what are the steps to write the code. So how FSM works in Verilog? So for that, this example we have taken 1011 in non-overlap method, and Moore we are taking. Okay, so for Moore we know how many states needed for this sequence. Okay, now our first question, like what ports it would need. It would need a clock, but obvious it will need a reset. Okay, it will need a 1-bit input, right? It would be a 1 bit, right? We are for sequence detector it would be always 1 bit. For output also it would be a 1 bit. So I've taken input X as my input, means X is my input, Z is my output, right? So there are intermediate variables two intermediate variables I would need, right? Those are PS and S, which are present state and next state. Okay, so you have to write it as reg. Okay, so this is kind of your shift register, or you can say your sequential logic. In the second slide, I've shown you the sequential logic. That's what this present state and next state will show. Okay, so we'll be using this intermediate resistors for that only. And why 3-bit I have used? Anyone have idea? Can you reduce? These are states, right? My present and next state variable. This PS and NS kind of shows my states.
We have to represent 5 states.
Yeah, right. So we have our states ranging from 0 to S4, right? 5 states. So 5 states will require a 3-bit, right? So that's why we have used a 3-bit. And rather than using 0001 in your case, you can use a parameter. Okay, this is a keyword given by Verilog. Okay, so rather than writing 000110, you can name it something. Okay, these things are already present in C also, if you are familiar with it. Rather than if you want to write somewhere 00, so you can replace it with S0 if you are defining it as parameter. Okay, so what does it help? Means what's the advantage of it? Readability, right? So you can read your code very efficiently if you want to reduce, or if you want to debug, it would be efficient for you. So I have used I've used only 4 states. So as we need 3 bits, so you have to extend it. It would be 3-011 for S3. Okay, so you make the change here in your code. Okay, so this is actually your task 1, that we are trying to model Moore FSM for sequence detector 1011. Okay, so just I have not written code here. You have to write that code, but I am giving you the syntax with some hints or with some comments. Okay, so ports, I have discussed what ports you will be needing, right? Clock you will be needing, reset, one input and one output. So you define those ports. Do the port definition, do the PSNS definition, means you have to replace by this. You have to use 2 registers. How much bit, that you know. Parameter definitions you have to do, means this line parameter S0, 2, you don't have to use 2, you have to use 3B000, right? Because we are dealing with a 3-bit parameter, right? And okay, over. Then we will be using a first always block. We have discussed the always block, multiple always block concepts. So this always block is for present state logic. This is important. Okay, so passage clock and then passage reset, whatever you want to queue, right? So begin and then present state is S0 when reset active. Okay, so when you will give reset at that time, okay, when your reset is high, you have to, your present state must be S0 or your initial state. That's what you have to code here. And in next line, your present state must change to the next state, which is derived from your input, right? Your next state logic, which is your next state, that will be defined by your inputs. That's what we have done in the state diagram, right? So your present state changes to next state, which is derived from the input when reset is inactive. Okay, so reset doesn't function here, but you have to assign something to present state. This is important, to assign to present state. Note this point. Okay, so what you have to code, that you see. Next we have a second always block. In that, what parameters we will be needing, on what value next, on what next state logic depends, right? That you have to write here. Then begin, then case, start with your case. You have to be present state, means your PS. just write PS here. And when it is on S0, so this is a statement, right? This is not code. Means there is no keyword like when it is on something. Okay, so when it is on S0, depending on what input is, you have to give your NS that particular state, right? So state by, if you have kind of know how your state diagram flows, then you have to assign it here, right, in that manner. So I've given an example. So if my input is 0, if x is 0, right, if you know, it would be like that, and it is equal to 1, right? So if this will execute, so when my x is 0, your next state is assigned as 1, right? Means your next state becomes S1. If your x is 1, then your next state will be S0, right? So in this manner you have to write how your next state logic will flow, right? How you have to evaluate your next state logic depending on your input, because you see the conditions are depending on input. If your x is 0, x is your input. So if x is 0, you have to see what you will get, right? And why I have used S0 here, let me disrupt this. Okay, this is for S0 only. So when you are on your S0, see where you will go when your input is 0, see where you will go when your input is 1. So this is what this kind of block of code represents. Similarly, you have to write it for all other state, S1, S2 to S4, right? So you know how many cases will or case statements will be there. Inside your case, how many expressions will be there, right? Different. And then we have our third always block. What is this? This is your output combinational logic. So it depends on present state. Sorry for the spelling mistake. So it depends on your present state only. Take the case of a present state, and depending on what your state of your FSM is, assign it respective output, right? So case PS I have taken. Okay, so what your present state is, at that time you have to assign your output. So at S0 your output is 0. What's your output when S1, when you are on S1, what's your output? When you are S2, what's your output? That you have to code it here. Okay, so this is your first task. You have your state diagram with you. You have to write its Verilog code.
Yes, anyone is having doubt in this? You can ask.
Because this is very important. One code of FSM you study very briefly, very nicely. Each line of code you try to get meaning of, right? If you are kind of very good with only a single code of FSM, for one single example, if you are very good with, you can model any FSM. But you must be very good with a single example of FSM. So please don't keep any doubt in this.